let's go ahead and talk about 1.2, paths, cycles, and trails. So in the previous lecture video, we talked about some basic properties of the graph, and we're going to continue on that route. So let's start with our first definition for today. First off, a walk is a list of vertices and edges in my graph such that if I had my graph, I can actually go ahead and trace this walk on my graph. I would be able to start at my first vertex and end at some other vertex. A trail is a specific type of walk. This is a walk where I do not repeat any of my edges, whereas a path is a walk where instead I don't repeat any of my vertices. If I want to talk about a UV walk, trail, path, respectively, then this is again a walk, trail, or path where I start with the vertex U and then I end at the vertex V. A lot of times they're actually going to be focusing on a path for this term, which is why I'm going ahead and introducing this notation. If you ever see the notation Pn, this represents a path with n vertices. And we're going to have some examples coming up in a moment. The length of a walk, trail, or path, or even a cycle, is its number of edges in that walk, trail, path, or cycle. In particular, if my walk or trail is closed, then that means that the endpoints are the same. In other words, if I have a UV walk or trail, that means the U and V are the same point. I start and end at the same place. So to really get a grasp on this, let's go ahead and pull up our Königsberg City graph. So we have our nice graph with 4 vertices and 7 edges. Let's give some examples of a walk, trail, and path. Let's start off with a walk. Let's say I want an AB walk, but not a trail or a path. Then a good example of this may be if I start at the vertex A, go along E2, hit B, go along E6, hitting C, and then go back along E6, going back to B. In other words, I might look something like this. I start at A, I go along E2 to B, I go along E6 to go to C, and then I return backwards, returning me to B. In this case, clearly we repeated some of our edges and some of our vertices. So we are not a trail nor a path, but we're still a walk. Now, if I want a trail but not a path, then this means I don't want to repeat any edges. So one example of this, not the only example, would be if I went from A, went along E2 to B, went along E6 to C, and then I returned back to B, but through E7 this time. So I repeated my vertex B, but that's fine. For a trail, all I care about is not repeating an edge. I don't want to retrace my steps along an edge. Lastly, here we can also talk about AB path, and in this case, technically, a path is also a trail, but more importantly, we don't have any repeated vertices. I could do, for example, the simple path from A, going along E2, and finishing at B. This gives me an AB path. I didn't repeat any of my vertices in my walk. So this is just a quick example of what we might do. So let's go ahead and prove a quick lemma about walks, trails, and paths. So a very short statement, lemma 1.2.1. If I have a UV walk, then it must contain a UV path subgraph. Remember, whenever I say subgraph, that means if I take the same vertices and edges, there must be a path in there. Again, whenever I say UV walk, that means I started at U, ended at some vertex V. So we're actually going to go ahead and prove this. So to prove this, we're actually going to go ahead and proceed by induction on the length of my UV walk. One quick note is that if you're not familiar with induction, I do really recommend that you take a look at those refresher videos on proof methods found earlier in our Moodle course homepage. So for induction, we have to prove it for our base case first. Well, The smallest length we can have for a walk is length 0. So if my length is 0, a UV walk of length 0 must be a single vertex, u equal to v. In other words, I have this situation. I have no length at all. If I had an edge, that would imply that I have length at least 1. But in this case, here clearly, I already have a UV path. So for my base case, there's nothing for us to really do. Now we're going to continue through by induction hypothesis. So continuing our proof, by induction, we're going to go ahead and assume the claim holds for all walks that have length smaller than L. So I have some value L. I don't know what it exactly is, but I'm assuming up to some number, our theorem or lemma is true. So if this is true for all walks up to length L, what if I have a walk of length L plus 1? If I can prove this for L plus 1, then I can also do it for L plus 2, L plus 3, and so on. So let's get rid of one quick case. If my walk already has no repeated vertex, then we're done. Remember, a path is a walk that has no repeated vertex. So if I already have no repeated vertex, there's nothing for us to prove. Thus, we can go ahead and assume that we have at least one repeated vertex on our walk. And we're actually going to go ahead and use this concept. Before I actually read this sentence, let me go ahead and show you a picture. If I do have a repeated vertex, then I might have a walk W, capital W, that looks something like this. So here I start at U, through some type of walk, I might be repeating a vertex or something like that. I end up at V. So how do I prove that I have a path? So our idea is actually going to be a little bit very quick and nice. If I have this walk W where I have at least one repeated vertex, I'm going to start at U, and I'm going to move along my walk, capital W, until I run into some type of repeated vertex. So here, usually on my original walk, I might go from U to X, go around a circle, go back to X, and then continue forth. Well, what's stopping me from, instead of going around this circle, why not just continue forth to W directly? That is, let's go ahead and just ignore this extra work here. Let's take a shortcut to W. Well, from here, I can do actually the same thing. My original path went from W, went in this big circle, went back to W, and hit V. Well, why not just ignore this whole big circle and go directly to V, taking me here? Well, if I look at this, then I have a walk that is strictly smaller than L. I have a shorter walk. That's what I'm stating here. Well, if I have a walk that is that's length less than or equal to L, then by my induction hypothesis, my new shorter walk must contain a UV path. Again, this is by induction hypothesis. Remember that we assumed that the claim held for all walks that had length smaller than L plus 1. I looked at a walk of length L plus 1, and then I found one shorter than L plus 1 from this picture. Well, since W prime has a UV path, then that same path P must also be a UV path in my original walk W, thus proving our lemma. So this picture is going to be a main factor in how we prove this lemma. Alright, so now that we proved a quick result on that, what can we do with our paths, walks, and trails? So for our next definition, if I have a UV path, then I can say that U is connected to V. So this means if I have two vertices, U and V, if I can connect them some type of way through a path, then we can say that they're connected to each other. In particular, we can say that my entire graph G is connected if no matter which pair vertices I choose. It could be this pair of vertices or some other pair. That is, for every pair UV, I have a UV path. In other words, a graph is connected if every pair of vertices is also connected. The last definition I'll put for this slide is if we're not connected, then we say G is disconnected. So we have these definitions here. The next thing I'm going to mention is talking about maximal connected subgraph. And we saw this sort of term before in the previous lecture about maximal. Here, whenever I refer to a maximal connected subgraph, this tells me that I have a subgraph that's connected and is the largest possible subgraph without adding another edge in or another vertex in. And if I have a disconnected graph or a connected subgraph, either or, the components are its maximal connected subgraphs. So a lot of very formal terminology. Let's go ahead and pull up this quick example. I have this as one big graph. First off, I'm going to note that this is not connected. It's disconnected. The reason being that if I look at A to H, I have no path that connects me from A to H. That tells me automatically I am disconnected. Sure, I can find a path from A to B, but I can't find one from A to D, A to E, or A to any of these other vertices. In this one graph here, the entirety of all these, each of these connected subgraphs are a component of G. So A, B, C, this is one component. D, E, F, G, that's one component. And H is another component. So in this graph, I have 3 components for my overall graph. Speaking of connectivity, another thing that we might be interested in, speaking very broadly, is a concept of a cut edge or a cut vertex. So let's talk about a cut edge. And a cut edge would be an edge, and this should be or, not of. This is an edge such that if I delete that edge, then I increase the number of components. Or in other words, whenever I delete the edge, I am no longer connected. Same definition for cut vertex. If I delete this cut vertex, then I am no longer connected. And some other notation, if I want to write G minus E or G minus M, where M is an edge set, then this refers to the subgraph of G obtained by deleting that edge or that edge set M. In other words, whenever I write this notation, I draw the same graph, but I do not draw that edge E or that group of that set of edges. And then I can do the same thing with a vertex, with a slight change. If I do G minus V, where V is a vertex, this is a subgraph of G obtained by deleting a vertex V and all of the vertices, all the edges that are connected to that vertex. And I want to talk about an induced subgraph. An induced subgraph is if I have a subgraph obtained by deleting a set of vertices. So if I write G, and notice here I have these square brackets of T. This is equal to G minus T bar, where T bar is the vertices minus T. So in other words, the induced subgraph is created by, actually let's go ahead and look at this example so that I can reference this. So here I have a graph G, and here in this little dotted lines, I've circled some vertices T. The induced subgraph, or the graph G induced by T, is all the vertices I've circled and all the corresponding edges that are still within my circle here. So this would be an example of an induced subgraph. All right, so we've introduced a lot of definitions so far. The next thing I want to talk about is just a quick theorem about cut edges and cut vertices. As it turns out, an edge is a cut edge if and only if it does not belong to a cycle. in my graph. So this is actually a little bit of a nice result, and we can talk about the proof. And actually what I have for y'all is, what I want y'all to do is take a moment and see if you can actually prove this theorem. The proof for this is in y'all's notes. So if you want to double check and see if you can get the proof of this, this is a good practice example. And so this is actually the end of 1.2. We will be talking more about cut edges and cut vertices later on, I believe in chapter 4, where we'll be talking about connectivity. But for now, we're just introducing the concept. All right, so like I said, that's all for 1.2. See you in the next video.